OK, let's do one more. So it's kind of the same spirit as before. We're still going to play with integers and how they're represented in memory. So in this case, once again, the attacker is inputting some character array. They give you a pointer to the start of the array, and they tell you how many bytes are in the array. So same as usual, and same as last time. We're going to assume that these are honestly being reported, because that's how you pass in arrays in C. And here's what we're going to do. We're going to allocate a new buffer on the heap. So we're going to call malloc. We're going to take the user's specified length, and we're going to add 2. Maybe I want to add a null byte or add something else at the end of the user's array. So I'll add 2. It should be fine. And then I will copy the data from the user's array into my new array, which fits len plus 2 bytes. OK, and I guess down here, I'm going to put a new line at the end and a null byte at the end. So those are the 2 extra bytes that I allocated. So once again, this seems totally fine, because I'm allocating enough space, and I'm copying from the attacker's input to the buffer, and the attacker's input is of size len, and buffer fits len plus 2. So this seems totally fine. What could be the issue? But we have another integer-related issue that we have to be careful about. What if the attacker passes in a really, really big array, like size FFFF. Once again, that's some sequence of 1s and 0s. It's a valid length for this buffer. So what's going to happen? I'm going to take this number, which is len, and I'm going to add 2. So what happens if I take a number that's already all 1s and I add 2? Well, then it's going to overflow. So maybe you remember from CS61C, if I get to the largest possible representable number and I add 1, it's going to wrap all the way back around to the smallest representable number. So if I take something like all f's and I add 1, I'm actually going to wrap back around to 0. And then if I add 1 again, I get 1. So len plus 2 actually evaluates to 1. And what that means is I allocate a single byte. And then memcopy tries to copy FFFF, a huge number of bytes, from data, which is the attacker's specified input, to buffer, which only fits 1 byte. So once again, I'm writing past the end of the heap. I have another problem. This is slightly different from the signed unsigned vulnerability from before, because everyone is reading size t's. We're reading size t here. Memcopy is reading size t's. But the problem is we had an overflow right here. We took a really big number and we added 2, and it wrapped back around to the smallest representable unsigned number, which is 0. So these are called integer overflow vulnerabilities, and we have to watch out for these as well. If the user inputs a really big number and I add 2, it could cause the number to wrap back around to something like 0. And once again, now I'm writing a huge amount of data to a buffer of size 1, which is an overflow. So how do I fix it? Well, it turns out the fix is kind of clunky. You have to do all this stuff with checking if len is close to the largest possible number, and if it is, you might want to return. So it is clunky, but turns out sometimes, because of the way that C is designed and the designers didn't think about security, you have to write really clunky code like this just to get the code to be safe. So I don't even want to stare at this code. It's so gross, but this is how you'd fix it. You'd add some fix involving the largest possible number. And just to quickly repeat a question that someone had earlier, you might say, OK, maybe it's not realistic for arrays that are this enormous size to be passed in. But if you are not convinced with these examples, you can maybe go and try playing with different types. There's the type called int8t that represents numbers between 0 and 256. That could be overflowed just by passing in an array of size 255, which is more reasonable. It's clunky, but we'll do that.